topic today is role of thermal energy storage for decarbonization and cooling. In the current situation, I think we are all trying to reduce and mitigate the use of carbon emitting equipments, and our focus is to increase the efficiency of these equipments and try and possibly transition from CO2 based units. And in the domain of cooling, I would like to highlight today how thermal energy storage plays a very crucial role, and the increasing traction of this technology in a variety of domain within the cooling, and how possibly entrepreneurs and companies can use this as a tool to integrate within their cooling systems to see a significant reduction in the use of CO2 based systems or fossil fuel based systems. So I would like to walk you through various applications which are today commercially on the ground working and has made an impact using thermal energy storage systems. And I would like to begin with the first is how thermal energy storage can be used to reduce refrigeration based systems itself, how it can help in downsizing the equipments. Taking the example of firstly the commercial building air conditioning. In this landscape, I think we are aware that about 70% of electricity, the consumption of electricity, cooling takes 70% of that total component. And normally the cooling systems are designed for peak loads. So any building which works, which is functioning from throughout the season, unfortunately, the capacity sizing is done considering the month of July or the peak. Here, thermal energy storage system helps in shifting your loads to the night time when the period during which the ambient temperatures are lower, so the electricity costs are lower, so your chillers are functioning at a better COP. And also you can use thermal energy storage systems during the time when there is a power outage, or when your dependency on diesel generators are the highest. As you see in this slide, this is a typical air conditioning load pattern where the air conditioning load and the various other miscellaneous electrical load bifurcation is shown on the one end of the graph. And we see that about 60% is constituted by AC. Now, you can see with thermal energy storage systems, you are basically moving the cooling load from the daytime to the nighttime. So you are generating energy by refrigeration units, but running it for 8 to 10 hours and storing this energy in thermal storage banks. And these thermal energy storage banks can be used in the daytime. It is integrated with your chiller systems, so that when the strategy could be chiller first strategy, where you keep on catering to the demand with the chiller functioning continuously until a base load is reached, and post which thermal energy storage can come in. This also helps in your chiller units to work at a maximum efficiency, so the part load inefficiencies are also mitigated. Thermal energy storage systems are designed in the early stages in a building design, and it can play a role in reducing not just the refrigeration units, but also to downsize the electrical connected load. And that can also impact your overall connected load demand charges. So the energy cost that monthly an HVAC cooling system incurs can be reduced as much as 28% to 25%. That is the kind of impact when it has when you reduce the refrigeration system by 50%. The second area of curbing the emissions is transitioning from diesel based backup systems which are used for cooling systems. Now, these are not just for larger building HVAC or cooling, but also for smaller commercial chest freezers and chest coolers, as you see on the slide, wherein thermal energy storage systems are integrated within the systems, within these freezers and coolers, in order to offer backup seamlessly when there is a power outage. And when and therefore whenever there is a when your final consumption of energy is in the form of cooling, why use a diesel generator or an inverter based battery? Because any form of batteries, also lithium ion battery or a lead acid battery, has a much lower life cycle compared to a thermal energy storage systems. Thermal energy storage systems, generally, the materials used are um, natural natural minerals, or in most cases it is water based systems. So these are not chemically harmful. Even the production of thermal storage systems are ecological friendly. Transitioning to renewable energy. So when renewable energy based power generation systems such as wind, solar, or tidal, often they are dependent on intermittency of the day. So there is a limited time when the sun shines. There is a limited time when the wind blows at the optimum speed. Today, energy storage solutions have become a integral part of renewable energy, wherein these systems also require cooling. So energy storage systems are also designed to have active refrigeration and cooling. And in uh, and in the next decade, I think we would see a tremendous requirement or demand for cooling for these systems, and that would really stress our grid, and we would be more dependent on fossil fuel based energy unless we have means to promote renewable energy. And because renewable energy is all cannot be generated 24/7, there has to be energy storage, and these energy storage systems also require cooling. And that is where thermal energy storage systems come in to reduce the refrigeration load required by the batteries, because these batteries also do not require the power surges in this battery during the charging phase, discharging phase, also come intermittently. And that is the time when the sizing of the refrigeration systems that it demands is really high, and those peaks can be taken care by thermal storage systems, where you can store the cooling in advance and then utilize this. Re- on the renewable energy based cooling systems, also the electricity generated by the solar PV is in most cases is stored in a battery. And if your final consumption is in the form of cooling, you can totally prevent or mitigate the use of batteries and use thermal energy storage systems. Like in the image that you see, this is a 24/7 solar micro cold room, which is used in the first mile, wherein the electricity supply is intermittent. It is not reliable. You have solar power, and solar power is supported by thermal storage for the nighttime operations. And this works seamlessly to maintain 2 to 8 degrees Celsius to keep the farm produce fresh. And it helps essentially farmers enhance and preserve the value of the commodity and not come under distress selling. Waste heat recovery. Industrial waste heat recovery, as well as one of the uh, this is one of the applications. Shipping ships and larger yachts, which are stationed and docked on in the oceans. Today there are mandates so that these cannot be running continuously, and uh, the engines to be optimally functioning, unfortunately the diesel generators are continuously running to keep the engines warm. And thermal energy storage systems are being used to capture this heat during the operation of the ship, so that the ships can still be turned off, the engines or the auxiliaries can be turned off, and this heat that was captured during the operations can be used during the time when the ships are docked. This also helps in reducing pollution where the ships are docked, and so the areas and the countries which are mostly affected, which are on the coastal, these companies are working actively towards innovative ways in which the heat can be captured, and at the same time you do not have to have the diesel generator continuously operating. Combined heat and power systems. Now there are phase change materials, thermal storage systems which generate electricity from the heat. So that is where the role of waste energy to value comes in, wherein industrial heat can be captured, a low grade heat as much as 50 to 60 degrees Celsius can be stored and then reused for a room heating, for example, or a high grade heat of 150 degrees Celsius and above can be stored and then again reused. So the storage phase becomes very critical. You need systems which have high energy density, also occupies lesser volume, and that is where thermal storage can play a role. And today the heating systems are gaining a lot of traction, especially heat pumps uh, which generate heat, and their coefficient of performance depends on the time of the day and the outside ambient temperature. Heat pumps are utilizing thermal storage systems to store heat during the time when the efficiency is high, and but at the same time there is no demand, and therefore the thermal storage comes in as a unit to offer, to plug that gap. So when there is a high demand, thermal storage and the heat pump together caters to the heating, while when there is no demand, thermal storage acts as a useful storage medium. This is for free cooling. This example, I think, was also covered in the previous by the previous presenter. In certain regions and countries where the time of the ambient temperature differences are really high, but depending on the time of the day, phase change material plays a role to absorb the cooling when the nighttime temperatures are as much as say 17 degrees Celsius, and the daytime temperature when it starts to rise about 32 35 degrees Celsius. That is the time when utilize the captured or the stored cooling to supplement the air conditioning systems. Therein, you can reduce about 15 to 20% of your air conditioning system load, and these can be done. These are being done in various ways by integrating the thermal storage on the false ceiling or on the walls, by directing the outside air into this cavity, or directing towards the thermal storage systems. Thermal energy storage systems use various different temperature of materials, and by using these combination of materials, a variety of cooling needs can be catered to, from frozen category, chilled or controlled ambient, to thermal comfort, to solar thermal. So these are the possibilities that industry can utilize with thermal storage. Yeah, thank you.
Thank you, sir, for your informative session.